Picture a massive, totally impenetrable digital fortress. You've got, guards at the gate, laser grids in the hallways, and this state-of-the-art vault. You feel completely secure.
Right, it looks great on paper.
Exactly. But what you don't know is that the concrete in the foundation has been quietly rotting for like 16 years.
Yeah.
Someone literally left a master key taped under the front welcome mat and the guards at the door. They're happily letting people in just because someone whispered a secret word.
I mean, it sounds like a bad heist movie, but unfortunately, that is the exact reality of the threat landscape we are unpacking for you today. We spend just an immense amount of resources building these towering security perimeters, but the actual breaches usually happen because of fundamental structural flaws that we just forgot to check.
Yeah, and on today's docket, we have 3 distinct stories that perfectly illustrate that fortress metaphor. And our mission for this deep dive is to extract the practical impacts you actually need to care about without getting bogged down.
Right, exactly what you need to keep your network secure.
So first up, we are looking at a 16-year-old ghost bug in the Linux KVM hypervisor that lets a guest virtual machine just completely crash the host system. Second, we've got an incredibly sophisticated espionage campaign targeting university webmail servers.
That one is a masterclass in stealth.
Really is. And finally, an undocumented, hard-coded backdoor just sitting right inside consumer routers.
Okay, let's unpack this. Let's start with this ghost in the machine. What exactly are we looking at here?
Well, we are looking at CVE 2026-53359. The security researcher who found it, Hunwoo Kim, dubbed it Janiscape. And to understand why this is sending absolute ripples through the cloud computing world right now, we have to look at the specific architecture where this bug lives.
Okay, I'll lay it out for us.
It's a use-after-free vulnerability, and it's located inside Linux's KVM hypervisor. But it is not just anywhere in KVM. It's buried specifically in the Shadow MMU code, the memory management unit, which is this legacy code that KVM shares across both Intel and AMD by 86 systems. And looking at the timeline from the disclosure, I mean, this bug has been hiding in plain sight since August 2010.
Yeah.
That is the kernel 2.6.36 era. In software years, that is practically ancient history. But before we get into how an attacker exploits it, I want to make sure we really understand the mechanism. The Shadow MMU manages memory for virtual machines, right?
That's right.
So if KVM is essentially a hotel manager and the guests staying at the hotel are the virtual machines, how does this memory management actually fail in this scenario?
Oh, that's a good way to frame it. So if we use that hotel concept, the manager is responsible for assigning rooms, which represent memory pages to all the different guests. And to keep track of everything, the manager has a central ledger. Now, creating new tracking pages from scratch is computationally expensive. It takes time. So when the manager needs a tracking page, they look for an existing, recently freed one to reuse, just to save a bit of time. The fatal technical flaw here is that the kernel code only checks the frame number, the memory address, but it completely fails to check the role or, the type of that page.
Wait, so the manager's only checking the room number, not the room type.
Exactly.
They might look at the ledger and reuse room 101 thinking it's a standard guest room, when actually room 101 was recently converted into the hotel's high-voltage electrical closet.
That is the exact mechanism. 2 completely different types of tracking pages can share the exact same physical memory address, but they perform vastly different jobs for the hypervisor.
Wow.
And because the code reuses the wrong type of tracking page just by looking at the address, the entire ledger gets scrambled. KVM's internal records of which memory page belongs to which process are suddenly just fundamentally corrupted.
And when a system realizes its core memory records are corrupted, it usually doesn't end well, right? The manager realizes the ledger is destroyed, completely panics, and basically hits the big red emergency button, shutting down the entire hotel and kicking every single guest out onto the street.
Which translates to the host kernel panicking and shutting down.
Yeah.
And that crash is what the public proof of concept for Janiscape demonstrates.
Right.
A single malicious tenant renting a tiny virtual instance can knock over the entire host server, instantly taking down every other innocent tenant's VM on that same physical machine.
That is a massive denial of service.
It is, but a denial of service crash is actually the good scenario here. The technical depth gets much, much worse when you consider remote code execution.
Wait, how does scrambling a memory ledger lead to an attacker actually taking over the physical server?
Well, it comes down to what happens to that freed tracking page or electrical closet, right? If it gets handed out for another use before the kernel's cleanup process finishes its job.
Oh, so there's a race condition there.
Exactly. When the delayed cleanup finally happens, it scribbles a value into memory that it no longer owns or controls. Now, the attacker only controls where that write lands, not the actual data that gets written, but in the hands of a skilled exploit writer.
Yeah.
Even that tiny, limited primitive can be escalated. They can manipulate memory layouts until that rogue write alters a critical kernel function pointer, and that grants them arbitrary code execution on the host system as root.
So the guest completely escapes their virtual sandbox.
Yeah.
I mean, it makes total sense why Hyunwoo Kim submitted this to Google's KVM CTF program. They offer up to like $250,000 for full guest-to-host escapes because KVM is the absolute bedrock of massive infrastructures like Google Cloud.
Yep, it's the foundation.
But this brings up a huge question for me. If this shadow MMU code is 16 years old, why is a modern cloud server even using it?
It is a really great question, and it all comes down to a feature called nested virtualization. Normally, modern servers rely on hardware-based memory management built directly into the processor.
Let me pause you there for a second because the research notes mention acronyms like Intel's EPT or AMD's NPT. Don't lose me in the acronym soup. What do those actually do?
Fair enough, I'll keep it clear. Those stand for extended page tables and nested page tables. Basically, instead of the hypervisor software doing the heavy lifting of translating a virtual memory address to a physical one, the physical silicon chip does it.
Oh, okay.
Yeah, it is vastly faster and way more secure. So modern hosts bypass the old software-based shadow MMU entirely, unless, and this is the big, unless the host allows nested virtualization.
Meaning running a virtual machine inside another virtual machine, which, I mean, cloud customers actually demand, right?
Right.
If I rent an AWS or Google Cloud instance, I might want to run my own Docker containers or my own hypervisor inside the instance I'm paying for.
And that demand is the weak link. If a cloud provider exposes nested virtualization to a guest VM, the hardware can't always handle that like Inception-style layer of complexity. So it forces KVM to fall back and route the memory management through that 16-year-old legacy shadow MMU code. Yeah. By simply requesting a nested environment, the attacker opens the door to the vulnerable code path.
So for you listening, if you operate a by86 KVM host that accepts uncrusted multi-tenant guests and you have nested virtualization turned on, you are squarely in the crosshairs. What is the immediate mitigation here? Because the sources mention not waiting for an NVD CVSS score.
Right. The National Vulnerability Database takes time to analyze and assign an official severity score, but you do not have time to wait for that. SUSC has already rated this a 9.3 out of 10.
That's massive.
It is. You need to verify your kernel includes commit 81cc day 30B4E8, which was merged into the mainline on June 19th, 2026. The patch is remarkably simple, honestly. It just adds a role check alongside the frame number.
But the hotel manager now checks both the room number and the room type.
Exactly.
And what if someone can't patch their host tonight? Like, what's the workaround?
You turn off nested virtualization entirely. Just disable the kvmintal.nested or kvmamnd.nested parameter in your host configuration. It might break some functionality for your tenants, sure, but it completely removes the attack path.
It is just wild how legacy code can sit there acting as a structural vulnerability deep in the architecture. But, while Janescape required a researcher to do some serious archaeological digging in kernel code to find an opening in, our next story highlights a completely different approach.
A much more direct approach.
Right. Sometimes attackers don't need to dig through the foundation. Sometimes they just walk right through the public-facing applications that organizations rely on every single day.
Yeah, we are moving from the absolute depths of the hypervisor right up to the application layer, the front door. And in this case, we're looking at a threat intelligence report from Proofpoint regarding a threat cluster they call UNK Mesh Extraction.
And the targeting here is incredibly specific. They are going after physics and engineering departments at universities across the U.S. and Canada. Specifically, departments with national security ties, or those studying astrophysics and particle physics.
Highly sensitive stuff.
Very. Now, Proofpoint's telemetry points toward China-aligned and Russian state-sponsored actors. And I want to be really clear, here we are just the messengers relaying the threat intelligence. We certainly don't take political stances on this show. We're just reporting what the sources found. But it really highlights how valuable university research data is to global intelligence operations.
Oh, absolutely. Universities are massive repositories of pre-classified research and dual-use technologies. And they are notoriously difficult to secure because, academic environments fundamentally require open collaboration.
Right, you can't just lock everything down.
Exactly. So to get to that data, these threat actors are exploiting Roundcube, which is a widely used open source webmail solution. The attackers are chaining together two specific, now patched flaws. There's CVE 2024-40009, which is a cross-site scripting or XSS flaw, and CVE 2025-49113, a remote code execution or RCE flaw.
Now, this is where the mechanics get fascinating to me, because I think a lot of people hear email exploit and immediately picture an employee downloading a shady PDF attachment or, clicking a fake login link.
Right, the classic phishing setup.
Yeah, but this is an XSS flaw in a web browser interface.
Mm-hmm.
How does a malicious script running in someone's Chrome or Firefox browser bridge the gap to execute actual code on the university's backend server?
It is a brilliant piece of engineering, utilizing a payload the researchers named IceCube. Let's break down the kill chain. It starts with a highly targeted phishing email. Because of the XSS vulnerability in Roundcube's email rendering, the victim doesn't have to click any links or download anything.
Wait, really? Just opening it?
Just opening it. Merely viewing the email within the web client executes arbitrary JavaScript directly in their browser.
Okay, so the IceCube payload is now running locally on the victim's machine. What does it do?
Its first job is silent reconnaissance. It siphons out credential information and session cookies. But it doesn't just want a password because passwords can be blocked by two-factor authentication, right?
Makes sense.
It wants the active session. To get that, IceCube steals the user's CSRF token, the cross-site request forgery token.
Okay, let me see if I can visualize this CSRF token concept for you listening. It's like the wax seal a king uses to stamp official orders. The server, which is the kingdom, doesn't actually care who is physically holding the piece of paper. It only looks at the wax seal. If the wax seal is valid, the server assumes the order is a legitimate command from the king.
That is an excellent analogy. The CSRF token is the cryptographic proof that a request is legitimately coming from the authenticated user. Once the IceCube payload steals that wax seal, it uses it to weaponize the second flaw, the remote code execution vulnerability.
Ah, I see.
It sends a malicious post-authenticated request back to the Roundcube server, stamped with the stolen token. The server trusts the request and executes the payload, allowing the attacker to drop a web shell onto the underlying server itself.
And according to the report, they drop either a shell called Square Shell or a post-exploitation remote administration tool called vShell, which uses a loader called Snowlight. It's just an incredibly deep chain. But what really caught my eye in the research notes was the operational security built into this IceCube payload. They use something called deferred triggers.
Yeah, the OPSEC here is what separates a smash-and-grab script kiddie from an advanced persistent threat. The JavaScript payload actively monitors the user's physical behavior in the browser window. It literally hooks into the DOM events.
Okay, how so?
It watches to see if the user changes tabs. It checks if the physical mouse cursor moves outside the boundaries of the browser window. It even intercepts the logout button.
Why do they care where my mouse is? Like, what does that do for them?
Because they want to ensure persistence while simultaneously covering their tracks before you leave. If your mouse leaves the window or you try to log out, the malware triggers. It quickly reattempts the server exploitation just to guarantee its web shells are planted, and then, and this is the crucial part, it deliberately destroys your active session on the server. It forces a logout.
Wow. So by logging the user out, it essentially tells the server to close the session cleanly, which erases the forensic evidence of the malware-initiated commands from the active logs. It cleans up the crime scene before the victim even knows a crime occurred.
Precisely. It is a masterclass in stealth. And the primary takeaway for anyone listening who manages enterprise networks is a fundamental shift in how we must view mail infrastructure. Proofpoint noted that email delivery is no longer just the vector, right?
The webmail server itself is the target.
Exactly. Defenders have to treat webmail servers as critical edge devices. You must prioritize patching, monitoring, and defending them just as rigorously as you defend your VPN concentrators or your firewalls.
Because it isn't just an internal utility. It is a public-facing door directly into your internal infrastructure. Which honestly brings us to an interesting contrast. We just walked through the sheer complexity of chaining an XSS flaw to a CSRF token theft into an RCE, just to deploy memory-resident web shells and hide from forensics.
A lot of steps.
So many steps. But what if threat actors didn't need to build a multi-stage exploit chain? What if the hardware manufacturer just left the front door completely unlocked and taped the master key to the window?
Well, from the highly complex, we move to the painfully simple.
The CERT Coordination Center recently released a massive warning about Tenda. They're a Chinese network device manufacturer that is incredibly popular in the consumer and small business router space.
Yeah.
And an anonymous researcher found an undocumented authentication backdoor living in multiple versions of Tenda firmware.
Yeah, CVE 2026-1145.
Right, and it lives right in the web server binary,
Right.
specifically in the BTPD file. Here's where it gets really interesting. How does this backdoor actually function under the hood?
Well, it exists within the login function of the router's web management interface. Now, in a secure system, when you type in your password, the system hashes it in this case. Tenda uses an MD5 hash and compares that hash to the one stored in the system.
That's just the fundamental cryptographic trust model.
Right, exactly. But in this firmware, if that standard hash authentication fails, the code doesn't just reject the login. It triggers an explicit ifelse fallback path.
Wait, a fallback path for a failed password?
Yes. The firmware calls a function named getValue and queries the device's NVRAM, the non-volatile random access memory, looking for a hidden configuration parameter called sys.rsadmin.password.
Oh, no.
Yeah, it fetches whatever value is stored there. Then it takes the password the attacker just typed into the login box and it performs a direct plaintext string comparison against that hidden value.
Okay, let me visualize the absurdity of this logic for a second. It's like going to an exclusive VIP club, and there's a bouncer at the door checking IDs. You walk up and hand the bouncer a piece of paper drawn with crayon.
A very bad fake ID.
Right. The bouncer scans it and says, hey, this ID is completely fake. But instead of kicking you out, the bouncer leans in and says, look, since your ID failed to check, do you happen to know the secret password? And if you whisper the secret phrase from the club's hidden handbook, the bouncer says, oh, you know the word, come on into the VIP section.
And the bouncer doesn't even ask for your name. That is functionally exactly what the C code is doing here. It completely bypasses the MD5 hashing mechanism. If the plaintext string matches the backdoor password, the application overrides the authentication failure. It ignores the username entirely and immediately grants the session a user role equal to 2.
Which is full administrative access.
Full root access to the device's web management. The attacker can change DNS settings to route all your traffic to malicious servers, disable security firewalls, or just flash their own custom botnet firmware onto the router. And this can be done completely remotely if the web management interface is exposed to the internet.
It is essentially a skeleton key, hard-coded right into the plastic box, routing all your data. I mean, why does this even exist? It's hard to imagine a manufacturer intentionally building a backdoor for malicious purposes into a production device.
I agree, and if we look at the reality of global hardware manufacturing, this is almost certainly a catastrophic example of leftover debugging code or vendor maintenance features.
Like stuff they use in the factory.
Yeah, exactly. Often, engineers build these plaintext bypasses into the firmware so their support technicians can easily access devices when customers lock themselves out, or just to facilitate automated quality assurance testing on the assembly line. The catastrophic failure happens when they forget to strip that debugging code out of the final compiled binary before shipping millions of units globally.
And it's totally invisible to the user, right? Like you cannot see this setting in the admin dashboard.
Completely invisible. You wouldn't know it's there.
And as of right now, there is no official firmware patch from Tenda. So if you are listening to this and you realize you have one of these devices, or you manage a fleet of remote workers who might be using them at home, what are the practical mitigation steps here?
Well, since you cannot patch the underlying binary yet, you have to cut off access to the vulnerable interface. Step 1 is immediate disable remote management. The router's web interface should never, ever be exposed to the public internet. If an attacker cannot reach the login page, they cannot whisper the secret password.
Makes total sense.
And step 2 is to change the default LAN IP address of the router.
Wait, why does changing the local IP matter if remote management is turned off?
Because of automated botnets and malicious advertisements. Threat actors write scripts that automatically sweep local networks looking for default IP ranges, like 192.168.0.1.
Ah, the standard ones?
Right. If a user visits a compromised website, a malicious script can quietly ping that default local IP in the background, trying to hit the router from the inside. Changing the IP to something non-standard helps hide the device from opportunistic, automated discovery.
So disable remote management and change the default IP. Actionable immediate steps to lock the front door. And that actually brings us to the end of today's briefing. Let's quickly recap the 3 core takeaways for your security posture today.
Sounds good.
First, if you are running by 86 kVM hosts, you need to verify you have the latest kernel patches to stop virtual machine escapes or immediately disable nested virtualization. Second, treat your webmail servers like critical network perimeters. They are highly targeted edge devices and need aggressive defense. And third, lock down local router access to block hard-coded supply chain backdoors.
The overarching theme here, really, whether you are a major cloud provider managing hypervisors, a university administrator protecting research data, or just someone securing a home office, is that vulnerabilities exist at every single layer of the technology stack.
Yeah, from top to bottom.
From 16-year-old code buried deep in the kernel, to modern application logic flaws, all the way down to the physical silicon sitting on your desk. Absolute visibility into your stack is the only way to defend it.
It really is a constant balancing act. And, I want to leave you with a final thought to mull over as you go about your day. Today, we looked at a hypervisor flaw that somehow hid in open source code visible to anyone in the world who cared to look for 16 years before someone noticed the structural rot.
Incredible, really.
And we looked at a backdoor that was deliberately baked into closed hardware, totally invisible to the user who bought it. It really makes you wonder, As you sit there listening to us right now, how many undocumented features, legacy bypasses, and silent VIP bouncers are quietly running in the devices right in front of you, just waiting for someone to finally find them? The foundation might look solid, but you never really know who is holding a master key. Thank you so much for joining us on this deep dive. Stay curious, stay secure, and we will catch you next time.